over to a part sampling system. Yes, I'm being recorded. I got it. And so if I make that visual, what's happening for a simple case with 4 sensors and the things coming in, we can see here's this little pulse coming in, and the red line shows that it's slightly later as I get from one sensor to the other. And so the conceptual idea, I always like to talk about the concepts first before we get into the equations. If I want to take this data and reconstruct the sound coming from that direction, I'm going to take what I recorded and apply the delays that would undo the delay for that direction. So I'm going to shift the signals in time a little bit so that anything coming from that direction will be lined up. And when I average across it, I get constructive interference for the sounds from that direction. And from all the other directions, I'll have either not fully constructive or even destructive interference as they get out of phase because the shift is wrong. And so the pulses don't line up. So if I put an equation that I say my beamformer output is some weighted sum of the pressure signal at each sensor with a shift where it's been advanced in time by some nominal delay for the angle I'm looking at, for theta naught is where I'm putting my attention, right? And so I can find that theta naught in terms of the cosine in that. So that's, again, the conceptual idea. Let's take the next step, as I often tell my students, now we have a concept of what we're trying to do. Let's be mathematical accountants and see if the books balance mathematically. Go figure out in more detail. So for these single frequency sensors, we can just use a vector of phasors that is complex numbers, because if I know what frequency things are happening at, the only 2 things I need to know then is what's the amplitude and what's the phase of that signal. And so that whole array of data at that frequency for a short time window, I can Fourier transform it. And I say, well, this delay in time becomes multiplying by a complex exponential. And then I have the same signal that's hitting all the sensors just with delays. That's my plane wave assumption. And so I plug in for my time delay to get this. And assuming things are narrowband and my sensors are at lambda over 2, I say the signal at the nth sensor is basically the propagating signal with some phase term that's due to the delay as I work my way across the array, just accumulating the delay. And so the whole array of observations for that time window I write as a complex vector that's the signal at that frequency, and then the phases for each sensor. We call this the phasor, or also sometimes the replica vector in sonar processing. And so if I'm going to process them, that part where I line them back up, I put that equation up again, I get the same type of thing. These shifts become the opposite phase. And so if I'm looking in direction T naught, this becomes U naught. The same type of thing, I end up with this sum across these, and it comes down to basically the difference between U, the direction it's really from, and U naught, the direction I'm looking. So if these 2 are the same, they cancel out, give me 0, and I've got e to the 0 as a 1. And I basically just got my scaled signal back, is the picture I drew for you. And so I can compactly represent this as an inner product between the array weights and the pressure vector, where the array weights are, again, these amplitudes scaled by, or with the phases, trying to undo the time delays. When I put all that together, you say, well, if I give you a set of array weights, how do I know how well they're working and how I'm looking? Well, we look at something called the beam pattern. The beam pattern is an array processing is just the analog of the frequency response, right? A frequency response tells me for an input that's a single frequency signal, how much gain is it going to experience by this filter? The beam pattern is the same thing for a unit amplitude plane wave. It says for a signal coming from this angle, how much gain is it going to experience? So for the simplest case, if I choose the weights to just be equal and average them, what that says is I'm creating constructive interference for the things that are coming straight at me at 90 degrees that hit all the sensors together in phase. They're already in phase, anything that's already in phase. And so 90 degrees, the cosine is 0. So this is 0 dB. It's full height here. As I move away from that, I get attenuated by 13 or more degrees, 13 or more dB. I get things attenuated as they come in at other angles. And then if I change the phases on these, I can change the look direction. Here, if I set these to √3/2, that's the cosine of what, 60 degrees, right? No, sine of 60 degrees, the cosine of 30 degrees. So I'm close to end fire. My angle is almost at 0. So I've taken this pattern and just shifted it and peak. And that's for those of you that know signals and systems, right, that's just the shift theorem from time domain in its spatial form. The beam steering is just modulating in space to shift things in wave number, basically. So let's make it a little more. What's another example of a spatial filter? When we were working on this, Andy Singer and I were out for a bike ride one day outside of Urbana-Champaign, and we came across this strange looking stop sign that looks like this. I'd never seen one like it before. And all of a sudden, Andy, I'm like, oh, that's a spatial filter. I mean, put it in context, you'll understand why do you need a spatial filter on a stop sign. This is a little road called Bluebill Road that joins up on 150 is the major thing going to the surface road. So this is like 50, 55 mile an hour road with a little residential street. If you're coming off this street, you need to stop and look for traffic before you get onto it. But they don't want all the trucks coming down this road thinking the stop sign is for them at that narrow angle. So if you're on Bluebill Road, you see this, the stop sign is at you, like you're looking right through the gratings. But as you move your way over to Route 150, you're looking at that and the stop sign has been filtered out. So I thought that was kind of a funny physical version of a spatial filter, right? And when we build arrays, we're really looking to do two things with it by combining spatial sensors. One is to filter things spatially, this idea that we can get constructive interference for things we want and then attenuate things in the directions we don't want. And then secondarily, we want to average down the background noise, any uncorrelated background noise, right? If you learn one thing in random signals and noise, you want to know that average uncorrelated things reduces their variance. So when I have uncorrelated background noise, averaging pushes the variance down. So if we come back to think more about this scenario, if I have signals and noise, let's think about that. So again, I have my sensors. I have a signal coming from this direction. And so I can write, again, that pressure vector is some replica vector based on the direction scaled by an amplitude. And now I've added some noise to it. So again, my mathematical assumptions is this is the complex amplitude of the signal with zero mean and some power. This is my plane wave for the direction I'm coming from that has all those phases in it. And then I have spatially white independent Gaussian because that's the simplest noise to model. And so why we, when we use arrays, what we're looking at, I'm going to show you a bunch of scenarios here, one after the other, where I generate 200 independent realizations of that variable, pretending I'm sitting here measuring my array for 200 measurements. And at 125 samples in, this low power signal with a variance of a half turns on, but I've got background noise that's loud enough. This is minus 3 dB. So if I'm just looking on a linear scale, like I'm going along, just looking at the signal, there's nothing, and then it turns on, and I can find that very easily. And often we're going to be looking at things on a dB scale. But again, if I start this on a dB scale, we see the signal turning on. But in the real world, we always have noise that's an issue, right? So if I put the noise on that's actually 3 dB louder than the signal, I'd have this going on all along. And it's not obvious from looking at a signal trace that I would necessarily see the change when that began. So this ability to spatially filter an average, we use something called the conventional beamformer. All right, so we're going to take that data, use the beamformer and the output. And the conventional beamformer is the thing I showed you at the start, the idea of just undoing the phases you expect for a given angle, making things coherent so you can combine them across sensors. It's also sometimes called the delay in sum beamformer. You may hear that as another name for it, right? But our weights in that case are just basically the signal we're looking for, then rescaled by the number of sensors, so our overall gain is 1. And when I apply that, my output power, I go through some math. I say my output power will be the power due to the signal, and then the noise power that's been reduced by a factor of n, which is the averaging, right? The reducing the variance because I've averaged these independent things. We call that the white noise gain. Right, so if I look at this, here's like if I made a single measurement at a single hydrophone or a single microphone, I don't see that signal turn on at 125. But when I combine, I think this was 50 elements in the array, you see the noise has been reduced enough that that signal really does jump out. You see a very clear ability to detect and see that signal. So this is why we like arrays, the ability to coherently combine signals we want while reducing the noise power. But and if it was that easy, we'd be done and it'd be time for lunch, right? It'd be much easier to do. But there's more to the story than that. In the real world, we have interferers, right? We're often out listening to things. So I'm trying. Here's something Shad says, because he's trying to soft spoken sometimes. I know Shad was a student at UMass where I teach, so I've known him for a long time. But Jen won't shut up. Jen's just going on and on here because she's very, very convinced she wants to tell me something. I need some way to null Gen out when I listen to Shad here, right? So I need something that can combine those weights, not just to make Shad constructive, but I need destructive interference for what Jen's trying to say here. And so, and you know, Jen started talking sooner, so she's much louder. She's going to overwhelm the signal I'm looking for if I look at a single sensor. So those of you that Jen didn't tell you the other part of my bio, when I'm not working on animal bioacoustics or arrays, I also have funding to do pedagogy. And I just cannot sit and lecture at you for an hour straight anymore. So we're going to do a little in-class exercise here, a big pair share exercise. The way it's going to work, I'm going to put up a question, and I'll look at my watch. And those of you online can follow along too. You're going to spend 1 minute thinking privately about what your answer is to yourself. And then after a minute, as the pair part, you talk to somebody seated near you, see if you agree. If you don't, try to convince the other person of the error of their ways or figure out what you did wrong. Again, it's just an exercise, no fisticuffs, no wagering. It's just for educational purposes. And then we'll talk about it as a group. Okay, so if we think about the case of I have a loud interfere with my 50 sensor array, and I'm steered my beam to broadside again. So this is my beam pattern. This is my gain as a function of the cosine of the angle in dB. The signal I want is the same one with the power by half at broadside, but the interfere is amplitude 10,000. So that's that's plus 40 dB, while this is minus 3 dB. But it's coming from the angle where the cosine is 0.06, and the noise is a gain of 1, so it's 0 dB. I want you to think about which of these three cases best describes what's going to happen. Well, you say the beamformer is steered at broadside, right? We have a nice, I'm showing just the positive half, it's symmetric over here. I have a nice gain of 0 dB, so only the source from broadside will be visible, because that's where I'm looking. You could say the interferer will have some effect on the output, but the source will still be visible. The interferer is like a little more noise. Or the third one, the interferer will completely mask the source signal I'm looking at. So I'll start my watch. So ponder that for up to a minute if you need to, and then I'll tell you when it's time to consult with your neighbor. And while you think, I'll steal a sip of tea. All right, so now take a minute and talk to your neighbor. See if you came up with the same answer between options 1, 2, and 3.
I do array signal processing. Yeah. Okay. So the 0.06 is the angle of interference. I think that interference is negative 15 dB.
And so that's at 0.6, right? But like the side lobes from 0 still way
So the right error, the right answer is that you got an element point you
So
All right, 10 more seconds, then we'll check in together.
Answer is 4.
Answer is 4. None of the above.
Just steer a no.
Oh, just right. Well, then we're getting there. This is why we need nulls. All right. So
I'm not going to.
What do we think? How many people said 1? How many groups think 2? I was very good. I didn't see any fighting here. That was good. Some effect was still. How many people said 3? A lot of people think 3. Ian, why did you say 3?
So my reasoning was that knowing that the interferer is 40 dB higher, but it's at 0.06, just looking at the side lobes from 0.06 versus 0, it's still way above like the minus 40 point, so it's still probably mass carry.
Right, so if I think about what's going on, well, this is actually at a half, so this is minus 3 dB on the log scale.
Oh, right.
So minus 3 plus 0 is the gain in that direction. I get out minus 3 dB of the signal I want. But as Ian said, I've got 40 dB of the thing I don't want, and I'm only shaving off maybe 13 to 15 of it. So it's still going to be like 25 dB, way, way louder than this. So it will mask the signal entirely. And as Nick was hitting, I overheard him talking to Jen. This is why we need nulling. So we'll get to that in a second. But the CBF will not detect the signal. If I look at the signal sensor or the beamformer output, all I see is this loud interference. Remember, that's Jen turning on at 75, and I never hear Shad start talking 50 samples later, right? And so here's the beam pattern working through what I just said. The output is the power unmodified in the look direction, only 15 dB down, like Ian said, or 13 dB down, and then the white noise is down enough too. So this is where we need nulls and adaptive beamformers. So in 1969, Capon came up with the minimum 4-inch distortionless beamformer. So it's more than 50 years old. I'll pause for a moment because I've been ranting about this for 3 years now almost. In 1969, what else happened? We landed on the moon, right? PBS couldn't tell you enough about Apollo missions for the whole year of 2019. Never once did I turn on PBS and see a Nova about MBDR, which was almost just as important in the history of technology. So I think beamformers are not getting enough credit in the history of science and technology. The space program gets all the credit. But anyways, the goal here is to choose the array weights that minimize the expected output power while still keeping the gain of 1 in the look direction, right? So I'm going to say I want to figure out what set of array weights I can make so my gain listening to Shad is still 1, but I'm minimizing all the other power, right? So that means whether it's loud interferers or just the reverb in the room or background noise, I'm using the weights the best I can to solve that constrained optimization with a Lagrange multiplier. And when you do that, the weights turn out to be the inverse of the covariance matrix, weighting the direction you're looking, divided by this term is a constant that just gives you the gain of 1 as opposed to something else. This is, as I tell my students when I teach arrays, this is where the action is. This is just the scaling factor. And so again, that's the expected received data of the pressure sensors, and this V sub naught is that phase vector in the look direction. So we get the signals we want unchanged, but if there are allowed attenuators, taking the inverse of that turns out to attenuate them. So when we do that, this is example. I didn't give I was on the slide, but I didn't say at the start. All these examples were developed by my friend Kathleen Wage at George Mason University that we collaborate with a lot. These are from her arrays class and some joint classes or seminars we gave at Portland State a few years ago. But again, the single sensor, it's invisible. And again, this is the conventional beamformer I just showed you. It's not great. But if I use the MBDR weights, if I know the ideal covariance matrix, you do see it. That loud interferer, when Jen starts talking, I null her right out. And only later, then I do see the quiet thing turn on 50 samples later. The practical problem is, in the real life, I don't know the theoretical covariance matrix. Because what do I need to find that? Well, either a lot of data, or I need to know where all the things are already, which is what I'm trying to figure out with my array. So I do what signal processors do. When there's something in the real world we want, but we don't have, we try to average a lot of data to estimate it in some form of average in general. But in this case, it's the very literal form. I just take a bunch of these measurements of these phasors, and I compute that outer product and add them up and average them. And I call that the sample covariance matrix. And we'll see that the eigenvalues and eigenvectors of that will tell us a lot about the performance if I'm in a minute. But let me first show you the problem of why that obvious thing doesn't work. If I implement that from a sample version so that I'm estimating, I take 100 of those measurements to estimate the covariance, I get this pink line, and this pink line is not getting the job done the way the black line is. Right? There's no clear detection. There's a lot of noise through here. So taking raw MBDR, just averaging isn't good enough because there are just too many degrees of freedom in the problem for your data. Question?
Yeah, sorry, I missed this detail, but did you need to know the directions that Gabe and Jen were prior to this process, or is the beamformer figuring that out through this process?
The beamformer is implicitly figuring it out. Well, I need to know where I'm listening. So I need to know where Gabe or Shad is. They're kind of both
So
in
you
the
do
same
need
beam.
to know where
I
they
do
are.
need to know where I'm looking. In real life, what I'm doing on a powerful computer, I'm doing this in my submarine for every angle I might be interested in running in parallel. I'm running one of these for every possible look angle. But they're all naively parallel. So we worry about one angle, what's going on at one angle at a time, but then it just shifts. So I need to know where I'm looking, but what I'm trying to avoid doing is explicitly identifying where the interferers are. I want that to happen implicitly through this covariance matrix or an estimate of it. And so, but when I try to just naively estimate it by averaging data, even though it seems like having 100 snapshots for 50 sensors ought to be good enough, it doesn't do a good job. There's just too many degrees of freedom in the data. And the reason is, in theory, this is what the eigenvalues ought to look like, the things that the matrix I'm inverting at the heart of this. In practice, the loud stuff is doing a good job, but the stuff that should be flat on the red line, some of it's higher and some of it's lower, because it's kind of a random thing. And the problem is this stuff that's getting small, when I compute the inverse, gets really big and it amplifies the noise. And so I need to find a way to avoid that happening. And that leads me to the dominant mode rejection beamformer. In passive sonar, this is one of the common algorithms we use to avoid that problem, which basically is based on the insight I just told you, that Doug Abraham and Norm Owsley 30 odd years ago said, our problem is not with the loud eigenvalues. Like, we're finding the loud things and doing it pretty well. The problem is all these small things that ought to be constant that aren't, assuming we're making this assumption, our background noise should be flat. So we're willing to impose that constraint on our covariance matrix. So we're going to break this up into two subspaces. We're going to leave the loud stuff, that's the dominant space, alone. And in the noise space, instead of using the individual eigenvalues, we're going to set them all equal to a constant by averaging them. So if I go back to this picture for a second, I'm going to take all of this stuff and just average it and hope that's a good estimate of where that flat red line ought to be. But then the question is, well, let me first show you when we know what we're doing, we use that for that. We basically use the same Capon formula, but with this constrained covariance matrix to avoid getting those really small things that get inverted by using the averaging. And that works much better. If I now go from my single sensor, the same thing I was showing you, but I've added this light blue line that's DMR, you'll see that it's because it's got fewer things to estimate, it does a good job of nulling the loud interferer. But then when Shad starts talking, I do see this come up. Because in imposing that constraint, I've reduced the degrees of freedom of the things I need to estimate. So I have a certain amount of information and I'm applying it more intelligently to parameters in the problem when it fits. But another way to think of it is I've moved my problem, which is I need to know when I look at that, well, in real life, how many things do I average? And this gets us towards the universal part. In the real world, the cost of not having this subspace dimension D is basically deciding how many loud interferers are there out there. And the cost of underestimating that is I've run out of notches before I've run out of interferers. So I've got several people all talking, Jen's brought all her friends, and I'm trying to cancel them all out. I've run out of notches. So to avoid that, in practical systems, this is usually built in, and it's set to be very conservatively large. So you're giving away some noise gain to do that. And it would be nice not to have to give that away when you don't need to give that away. If there are a lot of loud interferers, like I said, there's a big cost in not knowing them, but I'd like to be able to do a way to avoid that. So this is an idea Andy Singer and I brought into beamforming for a while. Andy had worked on similar ideas for linear prediction. It's a classic signal processing problem, but also has this what we call model order problem, which is to say, if I'm going to predict the next value from the recent history, the trick is, well, how many recent samples can you productively use? And Andy found a way to avoid having to make a guess at that by running over what's a universal strategy similar to what we had here. So what's a universal algorithm? A universal algorithm is something that processes the data sequentially, or some people would call that online, not batch processing. It's adaptive. In fact, Ryabko and others sometimes call them doubly adaptive, and I'll mention why. And this is a key thing. It converges asymptotically to the performance of the best algorithm in a competing set for every input sequence without assuming a probability distribution. You've all used it probably without knowing it. Zip. The zip utility is an example of a universal source compression. And then again, like 20 odd years ago, Andy and Mayor Fetter did this for linear prediction. And it stuck in the back of my head for years. There ought to be a beamforming thing we can do with this. And because I'm a slow learner, it took me almost 20 years until I was on sabbatical in 2018 to figure out how to do that for DMR. But that analogy was in the back of my head saying, In linear prediction, it has the same idea of how many samples should I be combining to estimate the next one. In DMR, we have this problem of not knowing how many interferers there are to choose that averaging for D. So that was my motivation. So if we come back to where we were a minute ago, when I showed you DMR, I start with a certain amount of array data, form my covariance matrix, take the eigen decomposition, and then based on that D, I average the noise stuff, combine that with the look thing, and I get a set of array weights. And my problem is I don't know what the right value of D is in general. Again, if I were allowed to go in batch mode, I could go home and try all the Ds and tell you which one works best. But I want to find a way to avoid that. So I say, what if instead of picking one D, I ran many of them in parallel? And you look at that and say, wait a minute, you were going to make it better and you made it worse. Right now I've got M different set of array weights and I don't know which ones to apply to that. And I said, well, don't worry, you don't have to pick one. I'm going to blend them together. I'm going to set a set of coefficients. And so my array weights for my universal algorithm will be some blend of all the possible choices of D over some range. If you like financial applications, this is a beamformer hedge fund. I'm investing in the different sets of array weights based on recent performance, who's doing well right now. So that's the intuition behind it. The trick is, well, how do you pick these array weights so that you're guaranteed to do well? Or how the blend weights, right? How do we decide how much to weight each beamformer? Well, let's think again about when we know from what capon when a beamformer is working well. So again, I have two beamformers looking in the same direction. So these array weights both have the constraint that they have a gain of 1 when I look at shots. And I'm trying to figure out, well, who's doing a better job of canceling out the other noisy people and the background in the room? It's the one that has the least total output power, right? Remember, capon's metric was we want to minimize output power subject to unity gain. So whoever's been doing that well is the beamformer that's doing the best compromise between not canceling interferers and averaging out the background noise. That they're not trying to, or they're doing the best job balancing those two. So if I look at those two beamformers, I look at the total output power, that's the weights times the data magnitude squared averaged over time. Wherever, if this beamformer is less power than that one, that means I should be weighting it more in my blend. I should be paying more attention to it. Again, the analogy came from the prediction stuff. Like if I have a whole bunch of weathermen telling me what tomorrow's high temperature is going to be, over time, I could look at each of their mean squared errors. And over time, I'd say, my prediction, I'm not going to try to make my own prediction. I'm just going to give you a weighted average of all their predictions. And I'm going to put more and more weight on the weather person who's more accurate as time goes on, right? Who has the smallest mean squared error. I'm trying to minimize this loss function. So how do we do that? Coming back, I said my array weights are that blend of the individual choices of the competing set. It turns out I use the softmax function. So this is where we see ideas from machine learning. So actually these were in some of the universal info theory stuff, I think, before I ever saw it in a machine learning paper. But it's the same idea of I have an exponential of the loss. So if the loss is large, e to the minus that will get small, and I'm not putting much weight on it. But if I have a smaller loss for one of the terms in this sum, it will be relatively much larger. This denominator is a lot of math, but it's just basically saying make sure the mu's add to 1, and the loss is the total output power for that direction so far. And so if I think of it, what I'm saying is I'm now taking this performance from each of them with the data and using that to adapt these things. And that's why it's called doubly adaptive. But first of all, each of these sets of array weights are an adaptation for a fixed choice of the subspace. And then I'm adapting across those adaptive array weights. Is why Ryabko called the predictors of this form doubly adaptive. And this leads us to a theorem that's remarkable, and that it provably says if you do the array weights this way, you are guaranteed to rival the best beamformer in the set. So if I think of as long as they all have the same look direction, and I limit the norm on all of them, which I often do in beamformers anyways, because it controls sensitivity. It says that the total output power per sample of your universal beamformer will be less than the best one you could have chosen in hindsight out of all those fixed competing options, plus a penalty term that is fixed in the numerator and vanishes as your amount of measurements n gets larger and larger. So as n gets larger and larger, this term gets smaller and smaller, and you're saying your universal thing has to be getting closer and closer to the best one you would have picked if I let you run in batch mode. But you're not running in batch mode. You're doing this all the time. And this convergence is not in the average, but it's for every finite power sequence. So that really gets attention when you talk to people who build radars and sonars, saying that because everything is finite power, if nothing else, because I start clipping. So being able to tell them for any sequence of data, I can do as well as you would have done for everyone. The way zip does just as well, compressing all the data, regardless of what the original model was, if you give it enough data. So exploiting some of the same, I am a kind person. I'm not going to drag you through that proof here and now, even though it's one of the hardest things I ever proved. But it does all work. I'd rather show you how well the algorithm works on for simulated data in real time. So here's a hard sonar scenario. This is time coming down the graph. This is that angle in directional cosine. And I have a quiet desired signal at broadside that's about 10 dB below the background noise. I start out with one interferer, and then every 100 or so samples, another interferer shows up much louder than the thing I'm looking for. And these were chosen to be annoyingly non-optimal, that they're showing up in the side lobes over and over, the loud side, the peaks of the side lobes over and over again. I simulated this for a 20 sensor array, and I only gave it 15 snapshots. So a snapshot start. It's very challenging to try to estimate the covariance matrix. It's not even full rank. You have to regularize it with something like DMR. And so I ran this scenario through that beamformer I just said, where I'm estimating it for every dimension and then blending them together, and looked at the total output power of all the options. So after 1,000 snapshots, this is my total output power. And this is the different choices from 0 up to 10 interferers that could be present. So the lowest point, the best of the fixed ones, was 9. The universal matches it. And so it says basically my performance is just as good as that without the prior knowledge that by adapting to the data, I was able to do that. In universal algorithms, the difference between your performance, the universal algorithm's performance, and the best you would have chose has a wonderful name. The most poetical mathematical thing I've ever come across. It's called the regret. The cost between doing what you did and what you would do with 20/20 hindsight if you were allowed to process the data that way. So it's really, a beautiful thing about universal algorithms that you can prove the regret vanishes over time, right? Wouldn't it be wonderful if real life regrets were like that too, right? That you could prove they were going to go away over time, but they don't. So the question is, well, how is it doing just as well without that prior knowledge of the data? It's in the blend weights. Let's look at what the blend weights were doing. So now this is a plot where this is the different dimensions, like from 0 to 10 interferers. This is the time axis over the simulation, 1,000 snapshots. And then the height here is showing the blend coefficients. So they start out equally, but almost right away, the 0 version says, oh, I can't, this is just the conventional beamformer. It doesn't have any nulls. And there's an interferer there right from the start. So it's letting a lot of noise through, and it quickly, like exponentially dies off, and sort of the others pick up the slack. And then when the second interferer shows up, this one dies off, and the third. You can see this game playing out over and over again until, which one, 0, 1, 2, 3 starts to take over. It gets most of the weights until the fourth interferer shows off, and then it falls off. And over time, eventually it starts to like 8 a lot. That's that orange one that keeps coming up and keeps coming up until the 9th interferer shows up, and then this one takes over until the end. So you can see how by sort of readjusting its investment portfolio, if you like the financial metaphor, it keeps adapting as new interferers show up, and the people that aren't performing well get attenuated out of the mix, and I give more and more of my array weights to the ones that are doing well. And in case you're worried, well, that maybe I was cherry picking one simulation. Here's 1,000 of them that I ran. And so for each of these, the blue line is showing that I think this is the 90% confidence interval. This is the median, and this is the median for the universal over all of them. You can see on it, the median for the universal is better than any of the other ones, any of the other medians, and sort of within their error bound. In fact, if I look in 70%, almost 700 of those 1,000 trials, the universal one was the best, because none of these fixed ones is always the best, right? If these high order ones are not doing real well early on, they could be having more array gain, but they're giving it up to make notches they don't need because there aren't enough interferers. As time goes on, these ones are obviously doing poorly because they can't cancel all the interferers. So by varying between them, I can actually do better than the fixed best option. Not just that I'm doing as well, I'm actually doing better in this non-stationary environment. But as Bill Cooperman once said, MATLAB simulations are doomed to succeed. So we wanted to put this on real data too. Kathleen processed, she was part of the Philippine Sea experiment, this large O&R experiment. And basically, how well does this work in practice? We used the Phil C vertical array. In the currents there, it was basically the world's biggest bass guitar string. So this array was strumming, making interference in the acoustic range we were interested in. And so what we did is we put a test signal into the experimental data. So in MATLAB, we added a synthetic quiet signal to make sure we could pull it out of the real world noise. And also so that we knew what the amplitude was and the signal was, we could estimate SNR improvement from it. And because this is a data set of opportunity, there wasn't what we needed for a soft signal. But just for people who are familiar, this is Philippine Sea off Taiwan. In this experiment, there were 6 tomographic sources and a vertical line array here over 5 kilometers deep with different array spacing. But we're just focusing on this subarray at the top, the 30 hydrophones spaced by 20 meters. And we have several hour-long data segments. And again, we had both distant shipping noise in there, but also the cable was strumming, which was like a discrete interferer that was projecting sound into our frequency band. So if I look at, this is a frequency wave number spectrum. If you haven't seen these before, this is frequency on this axis. This is spatial wave number on this axis. So this is towards this wave, plane waves going towards the surface and down, and the color codes the energy at that frequency. And when I look at this, the white is the line between evanescent and propagating waves. The black shows our estimate. This is basically the bearing of the strum wave. You see these really loud points on it. And the red is the quiet signal we injected. So we injected these signals in this frequency band at this bearing. Each bearing, each angle is actually a different angle on this plot. And just to give you an idea of when this happened, we looked at a couple segments. Actually, I'm going to show you this one. I'm not going to do both in the interest of time. This is a current profiler that was located in the array. So this is depth and time over about, about 16 hours, no, 20 hours, so 8 plus 4, 12 hours. And so you can see this is the current in centimeters per second. So you have a strong current that's dying down as we go through the tidal cycle. And so the strumming was varying as it went through. Oh, actually, this is an animation. I can show you for each, as I go through those hours, you can see the strum varying. You can see it gets louder and quieter. You can see the distant shipping noise getting more and less visible. And so you can see, it gets very quiet for some of those. And then, okay, so now we're back to the strum. So again, this is the one we processed. Kathleen ran this through from that 1 hour late in the thing for a 30 element subarray using the 30 snapshots for the matrix up to 10. This is the hyperparameter, that's the learning parameter. And rather than do the total loss, she did a sliding window of the loss over the last 150 snapshots for this, trying to make sure, could we bring this out away from the strum? Because as you look at this picture, you're not seeing it. It's actually suppressed from if I took the red line away, the underlying signal isn't visible underneath. So at 30 hertz, there's a lot of variation in the strum over time. And so if we look at 30 hertz, well, these are the mu's. Instead of plotting it in 3D profile, she did a color graph. So these are 4,000 time samples over the hour. As I go from 0 to 10 interferers, how am I spreading my away weights? This is the mu, the blend weights rather. So from none at all to almost 40%. So early on, it says there's a lot of complicated noise here. I need to cancel 8 or 9 things. But as time goes on and the current dies down, the strum gets less complicated. And saying, sometimes 0 is effectively a conventional beamformer. Maybe I need 1 to 3 interferers, but I'm reducing the interferers, which is I'm making fewer notches, which gives me more degrees of freedom to average out the background. This is a spatial spectrogram of the vertical wave number against time. You can see this is the loud shipping in this middle part. This is the strum, these loud lines here. And this faint line in between we are pulling up is the injected signal. You can see that we're able to cancel things out enough to pull that up. And in fact, if I go, she did this in fact for many of the frequencies over the band where the strum was present. This is the average SNR for that synthetic signal, we could do it. So the heavy black line is our universal algorithm. You can see this is always the highest line. The conventional beamformer, the dashed line, is often doing poorly. And then each of these colored dashed and then solid lines are different numbers, 1 notch, 2 notch, 3 notch for those different choices of D. So you can see that the universal is at low frequencies, it's rivaling the best of them. At the high frequencies, it's actually maybe a fraction of a dB better than even the best of them. And often, if I'd done the conservative thing of just picking the biggest one, that's this heavy yellow line, I'd be several dB worse. But in many practical sonar systems, that's what happens to avoid risking that. So below 25 hertz, the strum was pretty consistent, so it makes sense one of them could converge well. This is just zooming in on it. So that's showing again as we spread it out a little bit more. That it's about 2 or 3 dB to the large order one, which would often be the default, and the others are close. So the universal thing, without prior knowledge of the strum, is still figuring things out on the fly enough based on recent performance to blend the best case. So I'll wrap up here. So again, the conclusion, the takeaway is this idea of working over an array of a set of alternatives and blending them together intelligently using the softmax function lets us actually use mathematical tools to prove this bound on performance, to prove that the universal blended thing will be arbitrarily close as n gets large to the best one you would have picked in hindsight. So I'll stop here for questions. I feel like I've said enough for today. Thank you.
I have a question.
Mhm.
So you started with your
Yeah, I
example.
told you, first one, loud one to talk. Sorry.
So, I got big shoulders, I can shoulder that. So you started talking that your noise was Gaussian
Right.
for your simulations. Then you went to real life noise.
Yep.
What was your signal?
Our signal was actually a Gaussian from a specific plane wave, as opposed to the noise is white Gaussian. And
Okay,
in fact, I could have said more about that.
okay.
Here, a lot of our noise in this case is very diffuse noise from distant shipping. This is the cone of angles that traps the distant shipping, and it's not quite the SOFAR channel this deep, but there's still a channel. So this is interesting to us. We were wondering how well this would work because it's not white Gaussian noise. This noise has some spatial correlation, but it's not perfectly correlated either. So that averaging those degrees of freedom, we're still reducing the variance for whatever statistical part of that noise is uncorrelated from sensor to sensor.
So would you expect, if you were to run this in a different scenario with noise of different characteristics, would your process perform just as well?
Yeah, nothing in this idea of the blending assumes Gaussian noise. It just says I have these set of competing alternatives that are all trying to minimize the output power. Whoever's doing that will get the most weight.
So it just doesn't matter what characteristics the noise
Does it
has.
really not matter? I can't prove mathematically it doesn't matter for any weird noise model you could think of, but any of the common things, it doesn't matter about the noise. And that's just beamformers in general, that you're averaging down the incoherent stuff with those extra degrees of freedom. So, and again, this is, I've picked one example to show you with this idea of being universal over how many notches do I need to cancel the interferers, but there are a lot of other degrees, a lot of other problems in sonar where you have that knob you're trying to adjust in real time. One of which is how many snapshots should you average depending on how fast things are changing in the environment. So I have other simulations where I showed that. I had a moving target and it cleverly changes its averaging window over time to react to the motion of a target. We also recently, one of my students, Savash Dem, did a paper on a version of this for covariance matrix tapers, which are a technique when you know things are moving to widen the notches so that you keep the interfere in the notch, even though it's trying to get away as you're estimating. It's not trying to get away, it's just doing its thing and moving. But it's annoying you by not staying in the notch. And so, but how much you widen, you don't want to widen any more than you have to because you're sacrificing other performance in the system. And Savash was able to show in his master's thesis that the universal algorithm works really well for that. So certainly any of the many problems in beamforming where you're looking over the family and saying, I'm still just trying to push down all the power outside of the unit, the beam I'm making to look in a certain direction. These algorithms should work well for that. Yes.
Is there any difference in how quickly this would converge if you had fewer elements?
How quickly it would converge to be fewer elements. It certainly affects the convergence of each of these or how many snapshots you need. I guess it would only, I guess it would indirectly come into the bound. Oh, let me get back to the more complete version of the bound. And that the smaller your array is, the smaller you would put this gain on the white noise, so it would be a smaller numerator here. It would converge a little faster, depending on, and this is, if you're familiar with beamformers, this is the white noise gain constraint, right? We often use this as a sensitivity constraint. Harry Cox and Zeskind and someone else has a paper showing that this is another very good way to control your array weight. So indirectly, it would show up in this term if you have a smaller array. Laura.
All right, well, you know my background, but everybody else, I'm a biologist, so I apologize if this is a very naive question.
But you spent 3 years in a really good signal processing lab as a
I
postdoc,
did,
so you
I
must have
did,
learned something
yes, but I still have naive questions. Okay, so I'm assuming that this is all using like the same hydrophone, so would either traditional approaches or machine learning, would there be any advantage if you used hydrophones that had like different beam patterns or different frequency responses?
Well, if you have a directional frequency response out of it, like your hydrophones had directional frequency response, I think you could still use the same technique. You just already have to think about that a little bit though. You'd already have some directivity from that, but it would also limit which beams you could steer, right? You could only use this in certain directions. It's not going to be able to make data where there isn't any. If you have a hydrophone whose directivity is already here, you don't need it to know things over there, but you also won't be able to look over there later if you want to change your steering to look over there. It won't help you for that. Question here, yeah.
Just in terms of practical application, do you need to have, a computer that is a supercomputer?
Oh,
for
great
ability, or
question.
is this
See,
something that anyone
You're
can
very
do?
shrewd, because I've actually only told you half the story. I mean, I know that's going to take you a whole hour to get through this type of story. Anytime you do these universal algorithms, it really goes in two phases, which is you need to find a loss function where you get the behavior you want and converges, running all this thing naively in parallel. And then you figure out how to make it computationally efficient. And the linear prediction version, for those of you that know signal processing, you may have come across the Levinson-Durbin recursion efficiently to calculate the fourth order linear predictor from the third order linear predictor. And this recurse up the order. You need to have good math, signal processing / linear algebra skills to find an efficient way. Once you do that, or what the right basis is, to find, well, I don't have the equation for the blend here, but to find the blend immediately without finding all the intermediate ones. And I know how to do that for DMR by using a recursion that's basically implementing DMR, for those of you who know beamforming, is a generalized side lobe test. So by subtracting one interferon at a time, you can do it recursively. But you're right. If you do this naively, you need a really powerful computer, especially if you're trying to do it at multiple angles at once. But I'm from the school of make it work and then figure out how to make it pass. So and there's a lot of interesting, useful challenges in getting to that. We're like for the covariance matrix papers, we can make it work. But one of the topics that Savash is working on his PhD proposal now is can we use the Slepian windows as a way to make it fast, because they are nearly, they're like, in an engineering sense, they're a good basis for all the covariance matrix paper windows that are used. They're not exact, but it's like a 90% approximate good engineering. So if we can make something that runs really fast, that's only a few dB worse than doing the naive version, that's probably something that maybe would be interested in buying. But you're figuring out a great research question of, depending on which family of things you're doing, how do you implement this efficiently? Is a great research question. Yes.
You modify or limit or design it differently for an active application as opposed to a passive?
Yes. I'm hesitating. I don't want to give you all my good research ideas. There are some really interesting things on. I have ideas of universal pulse compression. And pulse compression. We see there are times where match filter is your best option if you only have one echo in a white noise background. You can't beat it. But if you have multiple things but really low noise floors, you might want to have something that's more of an inverse of the for your pulse compression if you can afford the noise gate. And then how can you make a smoothly varying adaptive thing in between them? Is a problem I've thought about. I'm sure there are other people. There's a great, actually Tony and I were talking this morning, there's a great group in Norway have looked at this and others, a very similar algorithm called the low complexity beamformer. Andreas Austar, I'm blanking on the names. Their home was one of the other authors. I'm trying, but there are people who have looked at it in an active sonar context of how you may be choosing different waveforms. Another version of the universal problem that comes up in info theory is rather than, and problems where you're not, for whatever constrained reason, you can't blend, you have to switch. So you have to say, I made you pick one of the options, but you can still update your choice from time to time. So sort of like if it's the hedge fund thing, you can only buy one of the stocks, but you can change every week which of the stocks you're buying and putting all your money in. It's still better than being fixed to one stock for the whole time. And so there might be active versions and active sonar where you might want to switch your waveform based on recent performance. So again, that embarrassingly, like we got these results in 2018. We published a few conference papers. I still don't have the journal paper up. I just think there's this, these are really powerful ideas of bringing these universal things, particularly for getting this guaranteed performance for every sequence. Now, that have
We have a
lots of classic sonar and radar problems. I do have to put a footnote on that. You're guaranteed to do as well as the best thing you do in batch mode. There's no guarantee this is good. Like if you just have a bunch of processors that are not well suited to your data, you won't magically do better, but you won't do any worse than them either. There are times if you just have bad algorithms or really challenging data, you're not going to make something out of nothing. But at least you won't be doing any worse than these other options.
I think we have an online question.
Oh, online question? Yes. Laura?
yes, we do. The question was, could you extend this approach to other components of the beamformer? For example, if you had uncertainty over the steering vector, could you do a blend as you vary it?
That's a great question. I don't have an answer for it. I certainly haven't done it yet. But it does seem there might be ways to use that to mitigate uncertainty there. I don't know. Like I said, there's a lot of great, it seems like a good master's or PhD thesis waiting to happen to answer that, to find that.
There's another one.
I think we're just about out of time. So if you guys could join me again and please thank John.
Thank you.
People online, thank you for your time. And
Nice work, John.
Oh, Jim Simmons. Grad students who are going to lunch with John, just hang back and we'll go get you back lunch. So thank you. Oh, one other question is Michelle is ill and is there anybody here that would like to talk with John? We have an extra half hour in the afternoon today since Michelle is not here. If you would like to talk with John, just come talk to me and we're gonna get you into that half hour. Okay. So thank you for your time.